Welcome back for part 2 of resistance and current. So now we're going to talk about Ohm's law. So Ohm's law is the relationship between voltage, current, and resistance. Effectively, voltage is equal to, voltage is equal to current times resistance. Or phrased differently, current is directly proportional to voltage if resistance remains constant. So if you have something where the resistance stays the same all the time, then we can say I equals the change of voltage over R, which would mean that I and V are directly proportional. So current and voltage are directly proportional. So that brings up two new terms. The first is ohmic, and the second is non-ohmic. So ohmic is an object that follows Ohm's law, and that happens when resistance is constant. And if that's true, then current is directly proportional to voltage. So an example of that would be like wire. Wire always has the same resistance if it's the same diameter and material of wire and the same length. So if I have the same wire and run current through it, the voltage and the current, and attach to a battery, then the voltage and the current are going to be directly proportional. Non-ohmic is when resistance can vary. So this would be something that modifies its resistance depending on outside factors, like a battery. The battery's resistance can vary depending on how many other batteries are attached to it, or something like that. So it is a non-ohmic material. All right, so let's take a look at a basic circuit. So here's a basic circuit. A circuit requires a power source. A power source has a positive and a negative end where the charge can come from. In this case, we're using a battery as our power source. So there's our power source right there. And then that power source has to be connected with a conducting material. So a conductor would be like a wire. From the positive end to the negative end, or from the negative end to the positive end, same. So here is where my current would go. It is connected with a conductor. In this case, the conductor goes through and then all the way through the light bulb and then back out and all the way around. So that works as a circuit because it is a complete loop of conductive material. Now, one element that could be in a circuit is a light bulb. And you can see that a light bulb is really just a wire. It's a wire that comes in here and then travels up and then does a loop, 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 and then comes back down all in one continuous wire. Part of that wire, if it's thin, we call it a filament, but the current still runs through all of it. And then we can use like a light bulb holder to separate the side piece from the bottom piece. So you'd have a connector there and a connector here, and then the current would come in and then back out through each of those connectors. All right, so for a circuit, we are going to assume that wire has no resistance. We're going to call this an ideal wire. And that way, the only thing that will provide the resistance will be the resistor, right? Like the light bulb. So let's do an example. A 15 ohm resistor is connected to the terminals of a 1.5 volt battery. Draw a graph showing the potential as a function of distance traveled through the circuit, starting from 0 volts at the negative terminal of the battery. Okay, so let's start by sketching out our circuit. Here's our circuit. We have a 1.5 volt battery. There is our power source. And so that's plus 1.5 volts. Then it travels, and it starts at 0 here. Sorry, so that would be 0 volts right at the negative end. Goes plus 1.5 volts up here. Then it goes around here, continuing at 1.5 volts. Then it hits the resistor, and the resistor is where the voltage is going to drop. So now I'm going to see my section here going down negative 1.5 volts. And then it continues back at 0 all the way to the end. So if I were going to graph that, let's take a look at what I end up with. So here's my graph. You can see that on the y-axis, I've got voltage or potential, and that is going from 0 to 1.5 volts. And then the horizontal, the x-axis, is the elements of the circuit. So we've got battery, top wire, resistor, bottom wire. You could also think of this as distance kind of. So in the battery section, I am going from 0 volts at the beginning and then going all the way up to 1.5 volts. Then in the wire, I just maintain that same 1.5 volts. So I maintain my 1.5 volts. There's no change of voltage because there's no resistance in the wire. I hit the resistor section. Sorry, so just to clarify, that is where the end of the battery is. The resistor section starts right there. And then the resistor drops the voltage down to 0. And then finally, I've got the bottom wire. And the bottom wire, it's 0, and it just maintains 0. And then this piece, the end of the bottom wire, is the same as the negative terminal of the battery. So those two dots really connect to each other. It's a loop, a circuit. So I've got up 1.5 at the battery, down 1.5 at the resistor, and no change for the wires. And then part B, what is the current in the circuit? Okay, so now for current, I know that I can use Ohm's law, and Ohm's law was I equals change of voltage over resistance. Okay, now my change of voltage was 1.5 volts, so that was 1.5 volts divided by the total resistance in the circuit, and the resistance comes from the resistor. That would be 15 ohms. And this is part B. And so then the current equals 1.5 divided by 15, 0.1 volts divided by ohms, and then that converts to amps. So 0.1 amps would be the current all the way through the circuit, and that current would stay the same for the entirety of the circuit. Okay. So let's zoom up to the top, and we'll do a little stop and think. Two identical batteries are connected in series in a circuit with a single resistor. The voltage is 0 volts at the negative terminal of the lower battery. So right here, that one, that point is 0 volts. Rank in order from highest to lowest the potentials A to E of the labeled points, noting any ties. Assume the wires are ideal. Okay, so since the wires are ideal, nothing will change when it's on the wire. So the source of the potential increase is the batteries. So the first battery increases it by E. So up at here, that is going to reach E, or its EMF. Then it goes up again, another one. So up here, now I'm at 2E. And then I maintain 2E through B and through C. So that would be 2E and 2E. Then I hit the resistor and I lose all of that potential. So that potential decreases by 2E and goes back down to 0. So it hits 0 right there. D would be at 0, E would be at 0, and then I'm back to the beginning, and I can go up E and then up another E for 2E again. Okay, so there's my values. Let's rank them. So from highest to lowest. So highest would be my 2E's, that's B and C. So VB is equal to VC, and those are the big guys. So those are bigger than, the next one is A, that has a value of a single E, and that is bigger than 0, which is D and E. V sub D equals V sub E. All right, so there is my ranking in order. All right, let's introduce a new topic, and that new topic is power. So that was, I've got the power. From Everybody Dance Now, CNC Music Factory, classic, good one. Okay, so power is equal to the current times the voltage. And power is basically how much energy is being put out by a certain resistor or we could call it the energy dissipated per time. So dissipated means used up or sent out. So like generally we could think about this as like light bulbs. It used to be, before we had LED light bulbs, that the greater the wattage of a bulb, the brighter it would be. So you could kind of, technically the brightness is measured in lumens, how bright something is. But you could say, oh, a 60-watt bulb is pretty bright and a 100-watt bulb will be way brighter. So power is equal to the current times the voltage, and it's the energy dissipated per unit of time. Because it's energy dissipated per unit of time, we could say the unit is joules, which is energy, per time, which is seconds, so joules per seconds. And then we give that a new name, which we call watts, capital W for watts. So power is current times voltage. And then I could do some conversion. So really, this one is the big equation, right? That's the one that'll be on your AP physics sheet. That's the one that you can start from. And then we can use Ohm's law and substitute in for current or substitute in for voltage. And when we substitute in for current or voltage, then we can find some other options. So if I have current times voltage and I substitute in for voltage, so if I'm going to sub in for voltage, I could use V equals IR. And then I plug into power equals current times voltage, and I'm going to substitute IR in there, another IR. So that's I times R, or I squared R. So that's one iteration, and that's taking the voltage and going into that spot. The other option is I could sub in for current. So I could take current and sub that in for the current part. So current is equal to the voltage over the resistance. Then I sub in I in here, and that would be power equals voltage over resistance times the voltage. So V times V over R, which is V squared over R. So all of these are the same equation. They're all representations of power, current times voltage. Let's do a couple examples. Oops, not that one, please. Okay, so finding the power of a dim bulb. How much power is dissipated by a 60-watt, 120-volt light bulb when operated using a dimmer switch at 100 volts? So I need power. And the first one that I could think of is that power is current times voltage. I have two voltages, right? I've got 120 volts and I've got 100 volts. The thing is, I've also got a power, right? I've got a 60 watt. The thing is, if I use the current will modify, the current will change depending on the resistance and depending on the voltage. So current is not a great sub-in. So instead, I'm going to solve for something that remains constant. And something that remains constant in a circuit is resistance. Resistance is not modified. So instead, I'm going to use power equals V squared over R. Because I have the voltage, the resistance is what I could find, and then that would be a constant taking me to my next step. So when I plug in here, that would give me 60 watts equals 120 volts squared over R. So I multiply R over, divide by 60 watts, and I get R equals, let's see, that'd be 120 squared divided by 60 gives me 240 ohms. So 240 ohms as the resistance on a dimmer switch wire actually seems kind of reasonable. That was the same resistance that we saw in the light bulb filament in part 1. So that seems like it's in the right scale. So I'm okay with that value. Now I have a resistance and I have a new voltage. My new voltage is 100 volts and I need a power. So I'm going to use the same equation. Power equals V squared over R, which equals 100 volts squared over the resistance, 240 ohms. And that'll give me a final power of 41.66 or 42 watts. So 42 watts would be my total power on a dimmer switch. And that makes sense. If I push the dimmer switch down a little bit, it'll get less bright, but not like totally dark. So 42 watts instead of 60 watts seems like a valid option. Nice. All right. Let's do one more sample question. Voltage of a stereo. Most stereo speakers are designed to have a resistance of 8 ohms. So that's a resistance. If an 8 ohm speaker is connected to a stereo amplifier with a rating of 100 watts, that's a power. What is the maximum possible potential difference the amplifier can apply to the speakers? So the potential difference is the voltage. So I've got power, I've got resistance, I need voltage, so I can use that same equation. Power equals voltage squared over resistance. Plug in my values. 100 watts equals V squared over 8 ohms. Then multiply both sides by 8, gives me 800. Take a square root of 800. V equals square root of 800, which equals, oops, 28.28, or just 28 will do, volts. So that would be the potential difference, the voltage drop that the amplifier can apply to those speakers with their resistance of 8. And that's within the realm of possibility because normally the voltage that comes out of an outlet in your house is like 120 volts or maybe 110 volts, depending on the way that you were set up. I think we're set up at 120 here in Novato. So 120 volts, 28 volts is less than that. So yes, we could drop that down and make sure we're only applying 28 volts of potential difference there. Okay. So that looks good. All right, last one, a little stop and think about power. Ranking in order for power. Oh, and once again, it's on the V's and the R's. So I know the equation, power equals V squared over R. And I'm ranking them for power. So power equals V squared over R. Great. In this case, power equals 2V squared over R, which is the same as 4V squared over R. 2 squared gives me 4. For C, it would be power equals V squared over 2R, which is the same as 1/2 V squared over R. And then finally, for V over 1/2 R, power equals V squared over 1/2 R, which is the same as 2V squared over R. So if I'm going to rank them, let's see. Biggest is 4. So that one is my big guy, and that's B. So I'm going to do power of B is the biggest. And then second would be 2V, so that's D, power of D, and that's bigger than the next biggest is 1V squared over R, that's power of A, and then the next biggest, or the last lowest one, is 1/2, which is power of C. Okay, so that takes us to the end of power, Ohm's law, current, resistance, and voltage, or potential difference. If this is still feeling a little bit new and fuzzy to you, I'm also going to post my intro to circuits notes, and And that one we're going to like we'll talk about what each of these things actually means and kind of define it and go through how it's used. And then I'll do a big analogy of like water going through pipes and waterfalls. And that might help. It's one that I use for conceptual physics. And so I'll post that as well for us so that we can kind of make sure that electricity really makes sense. Once you understand it as a model, I think it's pretty easy, but it takes a while to like process and understand and figure out how it actually works. Okay. So I'll post that as well, and then enjoy taking care of those chapter 22 questions. Until next time, my friends.